Hello everyone. This is a continuation of the last video where we're talking about how to graph rational expressions. Now what rational expressions are is expressions that have a polynomial on top and also a polynomial on the bottom. Okay, last time we talked about the steps in graphing these. The very first step is number one, you have to factor the top and the bottom. After you factor the top and the bottom, you look for values of x that make 0. Those are your critical points. Values of x that make the y equal to 0 are the critical points. Now the critical points can be on the top of the fraction and they can be on the bottom. For example, if I have x minus 2, x plus 3 on the top, I have x minus 4, x plus 7. My critical points are going to be 2, negative 3, 4, and negative 7. Now the values of x that make the top 0 are your x-intercepts. Okay, and that's because, for example, when x is 2, and I plug it in here, 2 minus 2 is 0. That turns that into 0, which turns this whole expression into one great big 0. So when x is 2, y is 0, and I can plot that intercept. So I can plot one intercept is at 2, 0. Now the other intercept is going to be at negative 3, 0. Okay, now what about the values of x that make the bottom 0? Well, if I plug in 4 minus 4 is 0. And so then I have something over 0. And when I divide something, anything over 0, I end up with an undefined. Undefined really is infinity and negative infinity at the same time. So for example, 1 divided by 0, you could call it undefined, but I think more helpfully for graphing, you should think of this as infinity and negative infinity. It's two things at once, and those two things cannot be further apart. So for example, when x is at 4, if I plug a 4 in there, then that's going to turn this whole set of parentheses to 0, which turns the whole bottom into 0. We don't really care what the number on top is. We could find it out, but it's not going to matter because whatever it is, divided by 0 is going to be positive, negative infinity. So that's going to happen here at 4. That's your other critical point. Now this critical point is an asymptote, a vertical asymptote. And finally, our last critical point is negative 7. All right, and so then what we did in the last video is we tested values in between each of those critical points to test if it's positive or negative. And depending on whether it's positive or negative, that's going to affect the shape of the graph. So let's go ahead and just walk through that process really quick just to finish up this review. So we're going to try a number to the left of negative 7. Let's do negative 100. So if I do negative 100, negative 100 minus 2 is going to be negative. Negative 100 plus 3 is going to be negative. Negative 100 minus 4 is negative. It's going to be negative. So I have negative, 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 negative. That's going to turn positive. So on this side of the asymptote, it's positive. It's zipping up that way. Let me change colors. So it's going up the asymptote because it's positive to the left of negative 7. Any number to the left of negative 7 is going to be positive. But once I step to the right of that, let's try negative 6. If I try negative 6, negative 6 minus 2 is negative. Negative 6 plus 3 is still negative. Negative 6 minus 4 is still negative. Negative 6 plus 7. Now this one, because it's to the right of that, negative 6 is going to make that guy positive. And so all of a sudden we flip one of those signs, and by flipping one of those signs, this whole thing now is going to become negative. So that means on this side, it's on this side of the asymptote. And then I could check on this one. That one's going to be positive on this side, positive all the way to 2. After 2, it's going to be negative. And then on this side, it's going to come like this. And I could test a number in each of those regions, but if I did, you'd end up with that kind of graph. Okay, so that's a review from last time. Now, what we didn't address is end behavior. What happens when you approach infinity from the left and infinity from the right? So there are 4 different cases to consider. Case number 1, degree on top is less than degree on the bottom. So the bottom has a bigger degree than the top. Let's give an example of that. Let's do a really simple one. 1 over x. Well, this is to the 0th degree, right? And then I could do plus x to the 0th. This is x to the 1. So the degree on the bottom is bigger. And you all remember 1 over x. As I approach infinity, you end up going like this, and you end up going like this. So as I approach infinity this way, if I put in an infinity, right, if x value is infinity, and I put that infinity right there, 1 over infinity is equal to 0. And if I put in negative infinity in there, 1 over negative infinity is also 0. Okay, so if the degree on the bottom is bigger than the degree on the top, like 1 over x, then it's going to be like this. It's going to approach that. And it might approach it differently. Like if I do 1 over x squared, then that's going to end up looking like this if I was to try those points. And it's going to have its asymptote right there on the y-axis. Okay, now you might have a chunky polynomial on the top. Let me do this, and this one might seem a little counterintuitive, but let's look at it. Let's say I have 1000x plus 701. Pretty big numbers, and on the bottom I have x squared. Now, in the short term, like when x is, let's say, 1, that's going to be 1007. That's going to be really, really big. So when x is 1, the top is huge and the bottom is super small. So on a graph, it's going to be really big, right around the neighborhood of 1 or 2 or 3. But once you get x to be really big, it's the power that tells you who's going to win in the long run. And as long as this power is bigger than this power, this bottom will always dominate. So think of, for example, a billion. On the top is 1,000 times 1 billion, and that's a huge number, obviously. But on the bottom, you have 1 billion times 1 billion. And a billion times a billion compared to 1,000 times a billion, well, clearly a billion times a billion is much bigger. So then this is really big, and this is a lot smaller in comparison. And small divided by big tends towards 0, right? You have one little tiny birthday cake for a billion people, a billion times a billion people who come to your birthday. They're not going to get much cake, right? So if the bottom is big and the top is small, you end up going to 0. So if you have some polynomial, like x to the 7th plus 3x to the 9th plus 500, and on the bottom you have x to the 8th plus 9x, then in the long run, this will dominate. And so the end behavior will look like this. It will tend towards infinity, and it might go like that. I mean, it'll tend towards 0. It might go like that. It might go like that. You'd have to test your signs. It might kind of bounce back and then go, but eventually it's going to tend towards 0 as you approach infinity. Okay, so that is the case when the top is smaller than the bottom. Case number 2. Case number 2 is when the degree on the top and the degree on the bottom are the same. So an example of this, let me just write this. Degree of the top equals degree of the bottom. So as an example of this, let's do this one. Let's do 7x squared plus 10x plus 100. And on the bottom, we've got x squared plus x plus 10. So think about what happens in the long run. When you get to some number, let's do a billion again. So 7 times 1 billion squared plus 10 times a billion plus 100. On the bottom, you have 1 billion squared plus 1 billion plus 10. Now, 7 times 1 billion squared. A billion squared compared to this one, this is so much bigger, we can kind of start to ignore this. At a billion, that's not going to make a whole lot of difference. Now, a billion is just nothing compared to infinity, right? If you do a gazillion or some huge number, or a billion times a billion times a billion, this is going to grow really, really, really quickly. These ones, not so much. So as you graph this one will have a lot more weight. Now this one right here. Now, you know how we're ignoring 10 and 100? Do we ignore the 7? Turns out the 7 is actually going to be pretty important, because we can basically call that, if we have a billion squared over a billion squared, these kind of cancel each other out and you're left with 7. Now, I'm not being super, super precise here. Let's do some long division and give this a little bit more precision. But basically, before we get into long division, I just want you to see something like this. If you see like 6x to the 5th plus a bunch of stuff, and on the bottom, 3x to the 5th plus a bunch of stuff, then ignore all of that stuff, and I just want you to focus on this part, and you can say, yeah, that will tend to 2. Just plain old 2 in the long run. So your graph, this is your x-axis, this is your y-axis. It might be bouncing around, doing all kinds of asymptotes, all kinds of intercepts, all kinds of stuff. But eventually, as you tend towards infinity, it's going to go straight to 2. So this line right here is 2. Eventually, it's going to find its way and it's going to follow that 2. Right here, it's going to go back and forth. That's going to follow 2. This is a really bad drawing, but you get the idea, right? There's a lot of crazy stuff that'll happen, but it'll tend towards that value. So let's go back to this first thing, and we're going to add a little bit more rigor to our discussion here by going back to our long division. So our long division is this. This is our divisor. We're going to put this under our little division symbol. And now, remember the steps. When we do long division, you divide. So you do 7x squared divided by x. 7x squared divided by x squared. And that just gives you 7. Now your next step is you multiply. So we're going to multiply across all those guys. That's going to give you 7x squared plus 7x plus 70. Now after this, you're going to subtract. So minus, minus, minus. That gives you 3x plus 30. Okay, and so that is your remainder. And our remainder we're going to put on top of this. So it's 7 over 3x plus 30 over x squared plus x plus 10. So this function, let me rewrite this. Our original equation, 7x squared plus 10x plus 100 divided by x squared plus x plus 10 is equal to 7 plus 3x plus 30 over x squared plus x plus 10. So as x approaches infinity, let's go ahead and plug in infinity here. 7 plus 3 infinity plus 30 over infinity squared plus infinity plus 10. Now, infinity squared is a lot bigger. So we have littler and then bigger. And as you get closer and closer to infinity, this one gets bigger and bigger and bigger relative to this one. And so this eventually goes to 0 as you approach infinity. And so your graph is going to be like this. If this is 7 right here, your graph might do all kinds of things, but eventually it's going to find that 7 and it's going to get closer and closer. It's going to make an asymptote. That 7 is an asymptote. So its end behavior, it'll approach 7. Okay, so let's go through the scenarios again. First scenario is like this. The bottom is bigger. Okay, the second scenario we just talked about is they are equal. So it's like x squared over x squared. And you might have like a 3 on top or something. Now the third scenario is where the top is 1 degree bigger than the bottom. So let's look at this one. X cubed over x squared. Okay, if I was to simplify this, x cubed over x squared, well, that's just the same thing as x. So overall, this guy is going to behave like that. In fact, it's going to behave exactly like that, except it's going to have a little hole right there at 0 where it's undefined. Let's do something that's a slight variation of that. What if instead of x cubed over x squared, it's x cubed plus 100, x squared plus 7x plus 99, and the bottom it's x squared plus 67x minus 2. Here, eventually, this guy will be the biggest, most consequential player on the top. This is the biggest, most consequential player on the bottom. And so this thing overall will look kind of like this. Okay, it'll look kind of like a line. Now, that means that what it'll have is something called a slant asymptote. And a slant asymptote looks like this. And so the graph might do something like this, but it's going to hit that slant asymptote and it's going to follow. And this thing might do something like this, but it's going to hit this and it's going to follow this. And so it's going to have that line, and we can find the equation of the line. Now to find the equation of the line, we have to use long division or synthetic division. So let's do an example of this. Let's say we've got x squared plus 5x plus 6 over x plus 4. And if we're graphing this, let's go ahead and see how we do on this one. We know it's going to have a vertical asymptote at negative 4. 1, 2, 3, 4. So right here we have a vertical asymptote. Okay, and then on the top, we can factor the top as x plus 3, x plus 2. So it's going to have intercepts at negative 3 and at negative 2. So at negative 3 and at negative 2. Okay. Now, this is the important part for the slant asymptote. We have to use, let's do long division. X plus 4, x squared plus 5x plus 6. When I do the long division, we'll put an x up there. Multiply this by both of those. That's going to give you x squared plus 4x. Now we subtract. And then we're going to do a 1, and that's going to give us x plus 4. We're going to minus, and we have a 2. And so our remainder is 2. We're going to put it over this. So that means that we have a slant asymptote at x plus 1. Let me talk about a little bit more about why we have the slant asymptote. Our equation, again, was x squared plus 5x plus 6 over x plus 4. By doing the long division, we showed that that's equivalent to x plus 1 plus 2, or was it minus 2? No, plus 2 over x plus 4. So as you approach infinity, this term right here becomes pretty irrelevant. For example, if I do some number, if x is really big, let's say like a billion, 2 divided by a billion, even a billion plus 4, imagine you have 2 cakes for a billion people who come to your birthday party. A billion and 4, it's not going to matter. No one's really getting any cake. So as x gets big, this becomes irrelevant, and your equation looks more and more like a straight line. So this whole thing, as you approach infinity, looks like this, because this part of it becomes less and less consequential the further you go out. So we have our slant asymptote, which is x plus 1. So x plus 1 is going to look like this. It's going to go like dot, 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 dot. And when we graph it, what's going to happen, if we check the signs, if I'm to the left of this asymptote, it's going to be like this. It follows that, and then we have a vertical asymptote. It's going to go down like this, and it's going to track that asymptote. Right here, it's going to go down this horizontal asymptote. It's going to hit this one, it's going to go back up, and then it's going to go hit that one. So in the long run, it's going to look like it follows this line, and again, this is your slant asymptote. And we found that by doing synthetic division. Okay, final case. Final case is where the top is 2 or more degrees higher than the bottom. So let's do an example. Let's say I have x to the 4th over x squared. Well, overall, this is going to be x squared, and so it's going to look like this. It's just not defined at 0. And if I have some extra bells and whistles on this, x to the 4 plus 3x cubed plus 7x squared plus blah, blah, blah. On the bottom, I've got like x squared plus 10x plus 1. I can ignore this, I can ignore this, I can ignore this, I can ignore this, because they're not going to be as important as this one is the most important on the top. This one is the most important on the bottom. And so this overall is going to look basically like x squared. So if I graph it, this one, we're not going to really worry about this, but it will have a quadratic asymptote, which means that the graph might do some interesting things, but eventually it's going to find this line, and eventually it's going to find this line, and the end behavior is going to look like this. Okay, so if the power on the top is bigger, like let's say this is x to the 5 plus blah, blah, blah. On the bottom, let's say this is x to the 2nd plus blah, blah, blah. Overall, this is x cubed, and we remember that x cubed graphs behave like this. So the end behavior means as you go right, it'll approach infinity. As you go left, it'll approach negative infinity. Okay, that's it. So this is everything about end behavior. Just send me a message if anything here doesn't make sense.